Hello, scholars, and welcome to Lesson 16, Session 2, on interpreting a linear function. So today our hope and goal is to be able to identify parts of a linear equation. We've already talked about this a lot. We're going to take the ideas of slope and y-intercept and we're going to give them kind of new words, ways of talking about them in hopes that it allows us to easily write linear functions and to compare linear functions as we go forward. So let's dive into it. Our problem today says Aretha is rappelling down the side of a cliff. The graph shows her height above the ground in feet as a function of time in seconds as she descends. The question is, what is Aretha's height above the ground when she begins rappelling down? And at what rate does she descend? So I think a lot of this is going to be fairly easy for you because we've talked about some of this before. For instance, at what's the height above the ground that she begins to rappel? We'll probably find that by finding the y-intercept, right? The starting value. So right here, it looks like the first value we see on the y-axis is at 90 feet. So at what height above the ground does she begin? She begins at 90 feet. And then going further, it says, what rate does she descend? And I imagine that's the slope, right? So we can pick any 2 points and calculate. We could pick this one and this one. It's really up to you. You can use slope formula to help you find this. I'm just going to use rise over run. It looks like we're counting by tens here, doesn't it? So down 10, and it looks like we're counting by twos here, yes? So down 10 and over 2, or you could even go down 90 and over 18. We're going to get the same thing. That's an H, I promise. Her rate of descent is, we'll call it down 10 and over 2, or of course we'll simplify that as -5. -5 what? Well, what did we describe our vertical change as? -5 feet over, what do we call our horizontal change? Our run. Well, that looks like it's in seconds. So she's descending 5 feet per second. Of course, she's going down. That's why it's negative. Okay, so let's use this information to write ourselves an equation now. So you know that this is going to be in slope-intercept form. And we've already got all the information that we need to be able to write that equation. So I'm going to do it nice and big down here because I'm going to write some additional notes down about this. So I'm going to say y equals, of course, our slope is going to be this rate, right? Our rise over run is going to be -5. We know that next to our slope is always an x, or whatever variable we're using. And then where we begin is going to be our y-intercept, so plus 90. Now, in this lesson, we're going to try to give these numbers some different words that just kind of help us understand them in context of a story. So we've been calling this number that goes in front of our number, we've been calling in front of our x, we've been calling it our slope. For today's lesson, let me grab a different color here. We'll just go with this nice pink here. For today's lesson, we're going to start calling this number the rate of change. And we've used that terminology before, right? We have used rate of change to describe slope and slope to describe rate of change. We've used them interchangeably. For our purposes, we're going to start using this phrase a lot more, just because it makes it so much more apparent what we're actually talking about. We're asking, how is something changing, right? A rate of change. And this number, of course, that's all by itself. We've got our slope, our variable, and then we've got this thing that we're going to call, we've still calling our y-intercept, but today we're going to start calling it as well the initial value. Because again, that's so much more apparent of what we're talking about. It's our starting value. It's what we start with, but they're the same thing. We're talking about the same thing. Of course, in context of this problem, we also need to talk about what our variables are. So, of course, this is our independent variable, right? I'll just write independent variable right there. And this is our dependent variable. In context of this problem, though, the x, and let's talk about how we figured that out. What is the x talking about? Because we need to know that if we're going to be able to tell a story using an equation. In context of a graph, it's really easy to look at your x-axis and look at your y-axis and know exactly what they are. If you don't know it looking at that, then you should be able to read the problem and figure out, like, what are the two things that we're talking about here? And last unit we talked about what are our two unknowns. But in context of this problem, x is specifically talking about the time in seconds, and the y is specifically talking about, we're just looking at the y-axis there, the height in feet. And I think a lot of this was apparent, but here's some vocabulary words that are going to keep coming up again and again as we move through these lessons. Specifically coming up, we're going to be comparing slopes and y-intercepts, or rate of changes and initial values, right, to one another given different problems. We're going to skip over a couple pages now because we pretty much talked about everything that I wanted to talk about from the next 2 pages. And I just want to jump to a few more of the application problems that we see on page 368. 368. So I just wanted to do a few with you, and then I'm going to have you do a few without me to get some additional practice on it. So this problem number 5 says the total monthly cost of exercise classes is a linear function. Ooh, all these words, we've heard function, now we're hearing linear function, right? Forms a straight line, and every input has exactly one output. So a lot of information in just those few words, right? So again, it says the total monthly cost of exercise classes in a linear function is a linear function of the number of classes attended. Okay, so the total monthly cost of exercise classes is a linear function of the number of classes attended. The table shows costs for 2 different gyms. Some questions about them. What is the cost per class at the gym? And which gym charges a monthly fee? And how do you know? Okay, well, let's answer this question first. What is the cost per class at the gym? Cost per class. Ooh, the word per, that is talking about slope, right? Or we could say rate of change. We're going to try to find the slope of gym A and gym B here. Now, it's important to remember how we calculate slope. Remember, slope is delta y divided by delta x, or a change in the y divided by a change in the x. It's really important that you never get in the habit of saying, oh, they paid $70 for 5 classes. That much must mean that they pay $15 per class, right? You can't just divide those two numbers, because what if there was an additional cost that was incorporated? Maybe this wasn't just a cost per class. So instead, we need to look at the change in the y, or in this case, the change in the cost, the monthly cost from 5 to 10 classes, and divide it by the number of classes, how that's changing, okay? So for gym A, it looks like, and if you don't know what this gap is, then do 150 minus 75, just y2 minus y1, right? But it looks like it's changing $75 every 5 classes. Again, you could do 10 minus 5 if you're not sure what that number is. And it looks like we are going to get that number that I talked about, 15. And what is that? That's dollars per class, right? What is this talking about? Per, what is this talking about? Okay, so gym A is $15 per class. Let's look at gym B. Well, again, we're going to say, well, how is this changing compared to how is this changing? Notice that this is the y values for the first one. This is the y values for gym B. So it looks like, and remember, if you're not sure, this minus this, 160 minus 110, that is 50 over, well, how's this changing? We already said that that's 5. It looks like that this is $10 per class. Well, that doesn't make sense at all, does it? Why would gym B be less money per class if these numbers right here are so much more than these numbers right here? Well, let's make sense of that, because this definitely has the smaller rate of change. This definitely costs less per class. So maybe we need to look at the gym's monthly fees. Okay, the gym's monthly fees. So basically, to figure that out, we need to figure out how much does it cost if somebody has taken 0 classes, right? It's kind of like we need to add in an extra spot here in this table. Maybe I'll use these dumbbells to do that. We need to put a 0 classes here. Now, one of the easiest ways to do this, and this table's set up really well to do it, is to just walk backwards. To walk backwards. This was changing by 75, and so I'm going down 75, down 75, down 75. Where am I now if I go one more step back, since this was counting by 5s? Oh, 75 minus 75 would put me at 0. It looks like there's no upfront cost. There's no monthly fee to go to gym B. But if I do the same thing here, down 50, down 50, down 50, down 50, it looks like I'm at $60. So let's say this, gym A, it costs $0 for the monthly fee, or we could say there is no monthly fee. But if we look at gym B, we see something different, right? We went down 50, down 50, down 50. It looks like having taken 0 classes that they already paid $60, and then they started paying $10 per class. And it took a while, but eventually that started to pay off, right? If you're taking a whole bunch of classes, if you're taking 20 classes, then it's going to cost you less at Gym B than it is going to cost you at Gym A. So let's say this. There's $60 for the monthly fee. I should have put Lee there. Monthly fee. Okay, so that's really important to be able to compare, right? Because imagine needing to pick between the two. If you're not going to attend very many classes, well, let's definitely go with Gym A. But if you're attending a lot, go with Gym B. I also want you to notice, how did we find the initial value or the y-intercept? To find the initial value, we need to make x equal 0. In the same way we did here, right? Look, to find the y-intercept, to find that initial value, what do? We looked at the y-intercept where x is 0. Okay, always thinking about when x is 0, when my independent variable hasn't applied yet, where am I? Okay, let's look at just a couple more real quick. Number 6 says the graph shows the distance in feet as a function of time in seconds. Write an equation for the function and describe a situation that it could represent. Include the initial value and rate of change for the function and what each quantity represents. Okay, so the initial value. And I want to keep reminding you, we're talking about the y-intercept here, right? We're saying the same thing. What is the initial value here? Well, that's easy. Where does it hit the y-axis, or where does it start? That is 30. 30 what? It is 30 feet. Okay, we're starting at 30 feet. And then we're going to ask ourselves, well, what is the rate of change? Let's remember that we're talking about the slope when we say that. The slope, okay, how do I calculate slope? I find 2 points that perfectly hit the grid lines. I'm asking how much do I go up and how much do I go over. It looks like I'm going up 30. We're getting from 30 to 60. And then it looks like it's counting by 5s down here. So 5, 10, 15. 30 divided by 15, change in the y divided by a change in the x, is 2 what? It looks like 2 feet per second. 2 feet per second. Well, what could this describe? It's linear. So if something's moving at a constant rate, it looks like it's increasing in height as time goes on. It's increasing in height at 2 feet per second. Well, what do you think that could be? I don't know. Is that I mean, it's definitely something that like isn't affected by gravity, right? And we're talking about seconds. I mean, maybe this is an elevator. In a tall building. And it's going up right now, isn't it? It's going up at 2 feet per second. I know it's tall building because it keeps going. It's going at least for 30 seconds, right? Maybe it's a really tall building. I don't know. But it's got to be something moving at a constant rate and increasing in height. Maybe it's like, I don't know, like maybe somebody is like lifting a flag up a really tall flagpole, or maybe it's a ski lift that's going like up the mountain at a constant rate. So just thinking about those elements, try to write yours. But we're going to continue on to this very last question. But it's all those elements. There's so much we can say now that we know so much about linear functions. This last one says, Mr. Seta? I don't know. I'm going with Seta. Plans a field trip for one of his classes. He rents one bus for the whole class and purchases a museum ticket for each student. The equation y equals 11x plus 400. And I hope that, like, having read that already, you're already like reading into this equation. You're already saying, oh, that 11, that must be talking about 400. Oh, that must be talking about, based on what we just read, he rented one bus for the whole class and purchased a museum ticket for each student. Okay, so equations should start jumping out to you. This gives the cost for the field trip as a function of the number of students who attend. What is the initial value of the function? Okay, well, the initial value, that's our y-intercept, right? That's like the starting point, is the thing that's not being multiplied by the independent variable. The initial value here is 400. What is the rate of change? Well, that's our slope, right? So we are going to say, what's next to the x? That looks like it's 11. What do these values tell you about the trip? That's the important thing that I want you to be able to say. Like, what happened one time? What do you have to pay right away? And what's happening over and over and over again? If I read this, he rents one bus for the whole class. And then he purchases a museum ticket for every student that attends. Okay? So we need to see in this what happens just one time. That's the cost of the bus. $400 he paid for that bus. Okay? And then what's happening over and over again? This is the amount per ticket. And we're just going to multiply that times the number of students. If you didn't know that just intuitively, we can read this. Gives the cost of the field trip, y is our, maybe I should say our total cost, gives the cost of the field trip as a function of dependent on, remember that language, dependent on, as a function of the number of students who attend. Is the number of students. That was a lot. I talked a lot. This video got way too long. I'm sorry, but I really wanted to do a really good job of being crystal clear about what I wanted you to hear. You're now going to do this sheet. If you read carefully, and try, you should be able to do this. You need to read all of this from this example, all of this, and then carefully read and find. So you're going to read, you're going to go back up here. You're going to explore this problem. What is the rate of change? Find the slope. What does this value represent? You should be able to figure that out, okay? If you read and try. Suppose there's no snow. What if this was 0, 0? What would the equation look like then? Okay, read and try. And then do the back as well. Good luck. Let me know if you have any questions.